The brain is often described as an organ of thought and emotion, but at its core, it is an organ of energy. Every thought, every feeling, every decision relies on a continuous and finely balanced flow of metabolic fuel, mostly glucose. However, when glucose availability fluctuates or is compromised, the brain doesn't immediately shut down. Instead, it turns to its emergency reserves, glycogen, stored primarily in astrocytes. These cells don't just passively hold energy, they actively manage its release, particularly through the astrocyte neuron lactate shuttle. This intricate energy-sharing system, once thought relevant only to cognition and motor control, is now being re-examined for its role in emotional regulation and mental health. The link between glycogen metabolism and mood disorders may be subtle, but it is increasingly compelling. At the heart of this relationship is the idea that neurotransmitter synthesis and signaling, processes critical for emotional regulation, depend on steady and localized energy support. Neurotransmitters like serotonin, GABA, dopamine, and glutamate require ADP for their production, transport, release, and reuptake. When neurons are under energy stress, even temporarily, these processes begin to falter. Astrocytes, through glycogen breakdown and subsequent lactate shuttling, can support neurons during these times, especially in regions of high synaptic activity, such as the prefrontal cortex, hippocampus, and amygdala, all of which are heavily involved in mood regulation. Disruptions in glycogen metabolism, whether due to chronic inflammation, stress, poor diet, or systemic insulin resistance, can impair this buffering capacity. Without timely glycogen mobilization, neurons may become metabolically unstable, impairing neurotransmitter balance and synaptic plasticity. Over time, this can manifest as mood swings, anxiety, cognitive fog, or even clinical depression. Studies have shown that during periods of intense emotional stress, astrocytic glycogen stores are rapidly mobilized, suggesting that emotional processing is an energy-intensive task and one that relies heavily on local metabolic support. Moreover, mood disorders themselves may feed back into the system. Chronic depression and anxiety are often associated with elevated cortisol levels, which impair insulin sensitivity and glucose uptake in the brain. This can suppress astrocytic glycogen storage and turnover, leading to persistent energy deficits in key brain regions. A vicious cycle emerges. Poor metabolic support leads to neurotransmitter imbalance, which worsens mood and stress, further degrading metabolic resilience. One particularly interesting angle is the role of glycogen in GABAergic function. GABA, gamma-aminobutyric acid, is the brain's primary inhibitory neurotransmitter, crucial for calming overactive neural circuits and maintaining emotional stability. GABA synthesis requires both glutamate and energy. When glycogen-derived lactate is insufficient, GABA production may be compromised, potentially contributing to anxiety, irritability, or insomnia. This might help explain why metabolic interventions, like ketogenic diets or fasting, which modify glycogen turnover and increase alternative fuel availability, have shown promise in reducing symptoms in some treatment-resistant psychiatric conditions. Serotonin, another key player in mood regulation, also depends on astrocytic function. The transport and reuptake of serotonin are energy-intensive and regulated by astrocytes in part through ADP-dependent processes. If glycogen reserves are depleted or astrocyte metabolism is impaired, serotonergic signaling may weaken, undermining emotional regulation. This could further explain why some individuals with metabolic syndrome, type 2 diabetes, or chronic high-carb diets report mood instability or are more prone to depression. What makes this all the more relevant is the rising prevalence of both mood disorders and metabolic dysfunction. In an era marked by high sugar consumption, disrupted sleep cycles, and chronic stress, all of which impair astrocytic function and glycogen dynamics, the mental health consequences may not be coincidental. Our emotional stability may, in part, depend on how effectively our brains can buffer energy demands through the precise use of glycogen stores. However, this insight also opens new doors. Interventions that support astrocyte health and metabolic flexibility may serve as adjuncts, or even alternatives, to traditional psychiatric treatment. These could include lifestyle strategies like regular exercise, time-restricted eating, omega-3 supplementation, low-glycemic diets, and sleep optimization. Pharmacological approaches that enhance lactate shuttling or support glycogen cycling in astrocytes may one day emerge as novel mood stabilizers. In the end, emotional regulation is not just a matter of psychology, it is deeply physiological. The energy stability of the brain, quietly maintained by glycogen shuttles between astrocytes and neurons, may be one of the invisible foundations of mental health. When that foundation weakens, emotional balance becomes harder to maintain. But by recognizing and restoring this hidden metabolic dialogue, we may find new and more holistic ways to treat, and perhaps prevent, the growing burden of mood disorders in modern society.